In this presentation, we'll look at the solution of differential equations using the Laplace transform. This will build on the material we had from our last presentation, discussing the zero input response, zero state response, and transfer function. Now let me remind you that for linear differential equations with constant coefficients, the Laplace transform converts them from differential equations to algebraic equations. And this is one of the primary benefits of the Laplace transform. So to start off our presentation, we're going to discuss an example. Our example is the system y double dot plus 5y dot plus 6y equals x dot plus x. The input is x and the output is y, and the initial conditions are y at time 0 minus is 2, y dot at time 0 minus is 1. The input x is e to the minus 4t u of t, and we'll note that x at time 0 minus is 0, since x of t is causal. It should be noted that the problem we're tackling has both an input and initial conditions. So here's the differential equation again. Y double dot plus 5y dot plus 6y equals x dot plus x. Now we'll carry out the Laplace transform and then do algebra. So with Laplace transform, we'll label the Laplace transform of x of t as x of s, Laplace transform of y of t as y of s. Then we Laplace transform each of the terms, and we use the differentiation rule for Laplace transform. So for two derivatives of y dot, we have the Laplace transform of y double dot. It's s squared y of s minus s y at time 0 minus y dot at time 0 minus. Plugging in our particular initial conditions, this is s squared y of s minus 2s minus 1. Laplace transform of y dot is s times y of s minus y at time 0 minus. Plugging in our initial condition, that becomes s times y of s minus 2. Now, the Laplace transform of x dot will be s x of s minus the initial condition, but the initial condition at time 0 minus for x is 0. So Laplace transform of x dot is simply s x of s. So we can plug all these back into our differential equation. Laplace transform our differential equation becomes quantity s squared y of s minus 2s minus 1 plus 5 times s y of s minus 2 plus 6 times y of s equals s times x of s plus x of s. Then collecting the terms, we have s squared plus 5s plus 6 times y of s minus 2s minus 11 equals s plus 1 times x of s. And we note that the terms minus 2s minus 11 come from the initial conditions. Now we'll solve for y of s. We divide through by s squared plus 5s plus 6, and we find y of s is equal to s plus 1 over s squared plus 5s plus 6 times x of s plus 2s plus 11 over s squared plus 5s plus 6. The first term in this expression is the zero state response. The second term is the zero input response. That is, the first term is due to the input and how it affects the output, and the second term is due to the initial conditions and how they affect the output. The term s plus 1 over s squared plus 5s plus 6 is the system transfer function. So you see the output is the linear combination of two terms, one due to the input and the other due to the initial conditions. We'll now recall that x of t is e to the minus 4t u of t for our example, and we'll take the Laplace transform of that using our table. So x of s is 1 over s plus 4. We'll substitute that into our expression for y of s, and we'll then perform partial fraction expansion. And after we've done that, we'll find y of s is 13 halves over s plus 2 minus 3 over s plus 3 minus 3 halves over s plus 4. Now we're ready to do inverse Laplace transform to get back to the time domain. So we'll use our table for that as well. And we find y of t is 13 halves e to the minus 2t minus 3 e to the minus 3t minus 3 halves e to the minus 4t, all times u of t. This is the response due to both initial conditions and to the input x of t. Okay, we have our solution for y of t, and what I want to do now is explore a little bit more about the initial conditions at time 0 minus. So, our result was y of t is 13 halves e to the minus 2t minus 3 e to the minus 3t minus 3 halves e to the minus 4t, all times u of t. And u of t was 1 for t greater than or equal to 0, so I can say that y of t is 13 halves e to the minus 2t minus 3 e to the minus 3t minus 3 halves e to the minus 4t for t greater than or equal to 0. And I've dropped the u of t here because I've specified the time limit as t greater than or equal to 0. The u of t would be superfluous. I'm now going to take the derivative of this for any time greater than 0, where the signal will be continuous. And so I find y dot of t is minus 13 e to the minus 2t plus 9 e to the minus 3t plus 6 e to the minus 4t. And now I'll find y and y dot at time 0 plus. So y at time 0 plus, plugging in 0 plus into the top expression for y of t, I find that to be 2. And y dot at time 0 plus, plugging into the expression for y dot, I find that to be 2 as well. Now I will refer you back to the initial conditions we used when we were solving the problem. We had y at time 0 minus was 2, but y dot at time 0 minus was 1. So I want to point out the difference here. Y dot at time 0 plus is 2, and y dot at time 0 minus is 1. So is there a contradiction here, or can this be explained? Why is y dot at time 0 plus not equal to y dot at time 0 minus? There's no contradiction here. It's because of the input. The input starts at t equals 0, and the input, x of t, equals e to the minus 4t u of t, has a jump in it at time 0. Now that jump causes the jump in y dot at time 0. So y dot is discontinuous between time 0 minus and time 0 plus. Now, if the differential equation did not have an x dot on the right-hand side, this discontinuity would not appear. But because it does appear. And the reason is because if x of t is discontinuous at t equals 0, then x dot will have a Dirac delta in it. It is that Dirac delta which causes the jump in y dot at time t equals 0. One can show, by going through the exact math that we did before, that if the differential equation was y double dot plus 5y dot plus 6y equals x, you would not have a discontinuity in y dot between time 0 minus and time 0 plus. It's because the right-hand side is taking a derivative of the input signal, and because the input signal itself is discontinuous at time 0, that we find a discontinuity in y dot. In a moment, we'll switch to discussing the general case of the zero input response and the relationships between differential equations and transfer functions. But before we do that, I want to point out one thing again with regard to this particular example. We found before we partial fraction expanded that y of s was the sum of two terms. And I stated that the first of these was the zero input response, 2s plus 11 over s squared plus 5s plus 6, and this was due to the initial conditions. And the second term was the transfer function times the input. Transfer function was s plus 1 over s squared plus 5s plus 6, and the input was 1 over s plus 4. That was the zero state response, and that's due purely to the input. So we see superposition at work here. The zero input response plus the zero state response summed together make the total response y of s, here in the frequency domain. So now let's look at the general case of the zero state response of a linear time invariant continuous time system governed by a differential equation. So this LTIC system has the following differential equation written using the differential operator. Q of d times y of t equals p of d times x of t, where d is the differential operator. And q of d we'll write as a polynomial in d to the n plus a1 d to the n minus 1 plus through an, and p of d we'll write as b sub 0 dn plus b sub 1 dn minus 1 through to bn. So, to find the zero state response, we of course have all initial conditions 0. This is the response due only to the input. And we'll label the Laplace transform of x of t as x of s and the Laplace transform of y of t as y of s. Now, because it's zero state response and all our initial conditions are 0, we don't need to worry about those initial conditions when we take the Laplace transforms of derivatives. So, we have a much simpler result for the Laplace transform of derivatives. The Laplace transform of the rth derivative of x of t will be s to the r times x of s, and of course the Laplace transform of the rth derivative of y of t will be s to the r times y of s. Therefore, the Laplace transform of our differential equation q of d times y of t equals p of d times x of t is the following expression. We first have a polynomial s to the n plus a1 s to the n minus 1 plus through an times y of s equals the polynomial b0 s to the n plus b1 s to the n minus 1 plus through bn times x of s. And you'll quickly note that the first polynomial is q of s and the second polynomial is p of s. In other words, it's the same polynomial that we had with q of d and p of d, except now d has been replaced by s. So we find our differential equation has been transformed to q of s times y of s equals p of s times x of s. So in the case that the initial conditions are 0, it's quite easy to find the Laplace transform of a differential equation. We simply take the d in q of d and p of d and replace it by s. That gives us q of s and p of s. And therefore the differential equation becomes q of s times y of s equals p of s times x of s. From that point, we can find the transfer function. We divide the left-hand side and right-hand side by q of s, and we find y of s is p of s over q of s times x of s. Of course, y of s is the output and x of s is the input, and the relationship between the two in the zero state case is the transfer function, which we label h of s. H of s is p of s over q of s. So in the zero state case, we have a very nice relationship between the time domain and the frequency domain. In the time domain, we have q of d times y of t equals p of d times x of t. And in the frequency domain, we have y of s is equal to the transfer function p of s over q of s times x of s.